And
we are live.
Okay, so we are live. So thank you very much for joining. There is another session of Meetup, Ticino Meetup. So thank you very much for everyone that joined our streaming. So sit back and relax. Okay. So before starting with our talk, so please follow us in our social like LinkedIn, Meetup, and YouTube. So and we have actually also a website. So please follow us in our channel to be up to date with our new talks and things. Stupid things, obviously. So, and talking about stupid things, here we are, Riccardo Cardin. So Riccardo Cardin, I'm very happy to that Riccardo is here with us. Riccardo is my ex-colleague from my previous company, lastminute.com, and is an expert of functional programming and especially on the effects. So I have to be honest, fun fact, Riccardo maybe is the first person that introduced in our company effects, and so I think that he has something to say about that. So maybe something, maybe, and I will leave to you. I mean, to give a feedback about if it's important or not. So okay, so. After this, cringe moment, I leave the word to Riccardo, okay?
Okay, guys, thanks for joining, first of all, to this talk. This evening, we try to understand what are effects and what are effect systems. And we are gonna do in Scala. Okay, so we could have used another language, also Kotlin can implement effect systems, Java in some form, we will see, we have a slide, but Scala for sure is one of the language in which the community is more focused on this topic, maybe too much, okay, because there are a lot of people in the Scala community complaining that there are too many effect systems and too much complexity, okay, but we don't care, okay, we like to experiment new things. So first of all, who I am Riccardo, and I don't work with Scala, sorry, in my day-by-day work, okay, but I'm studying Scala and using in my articles that I write for Rock the JVM. I don't know if anybody of you knows the platform. Go and see the awesome job that Daniel, which is the owner of the Rock the JVM, is doing for Scala, Kotlin, and Java. And here are my references. If anybody of you wants to contact me, can on GitHub, LinkedIn, and I have also a blog. Well, so let's start. And the first question we are trying to answer is why we love functional programming. Clearly, we all know that the main answer is because we want to appear smarter to our colleagues. Okay, this is the main. Okay, no problem. The second,
there are no other reasons, so please.
Yeah, the second reason is that everybody wants to learn the language of gods. Okay, but the third reason, the one that probably have a return in your day-by-day work, is that is the substitution model. which means that if we have a function that we can call pure, okay, which doesn't call anything aside the function, we can substitute the result of the function to the at the code site. And this is why this fact is which are the advantages of the substitution model. Mainly it enables the local reasoning. So to understand what's going on with a function, I only need to look at its signature in the nirvana of functional programming, okay? But I can't understand a lot, okay, if I use the pure functions, okay, only looking at their signature, okay, and it enables referential transparency, which is basically more or less okay the same, but I don't want to go deeper with referential transparency because it's a tough topic. However, as we all know, we can't deal only with pure function, because everybody in its day by day work have to, I don't know, read some data from a database, call a microservice, an API. So shit happens, as we know for sure. So the main functions that we deal with in our everyday day by day work are impure, which means that they call the external world. And just to have an example of what the imperfect word is, we're gonna use this example, okay, the drunk flip function, okay, that basically it models a coin toss, but there is a twist, there is a gambler that might be drunk and lose the coin. So basically these 5-6 lines of code have to deal with a lot of what we call side effects, because here we are dealing with, for example, errors, exceptions, something can go wrong, and here with non-determinism. Every time we call the drunk flip function, we will have a different result, okay? And this kind of behavior are called effects, and to be more precise, they are called side effects. So the first definition we find is that a side effect is an unpredictable change in the state of the world. So in the outside of the world of with respect to our function. And why we don't like side effects? Because they are completely unmanaged. Okay, they just happen, and even a simple function as dividing through ints can fail. Okay, if b here is equal to 0. Okay, so we have to deal with side effects. They are there. They happen. They ruin our world. Okay, what can we do? But the best that we can do is to track the fact that a function uses a side effect, okay, can produce, sorry, a side effect, and try to push, okay, the execution of those functions at the boundaries of our system, when we can handle more easily the result of the side effects. And this leads us to the effect pattern, which is a design pattern of the functional programming, in which we define the effect, which basically is the good part of a side effect. So when a side effect is tracked and controlled, tracked means that, for example, in the functions, in the function signature, we can read the fact that the function can generate a side effect and can be controlled. So we want the side effect to be executed only in a controlled manner, in a what we call the end of the world, okay? And the effect pattern basically defines 2 points, okay? We need a type, okay, that should tell us what effect a function can perform, and which will be the result of the function, okay? as we said, for example, the drunk flip deals with non-determinism and error. So I expect a type that can tell me that the drunk flip can fail with an error, or can have a different result for different codes. Okay, and the other important thing of the effect pattern is that we want completely separate the description of what we want to execute from its execution, and this is called deferred execution. Okay, basically, so a function, calling a function does not mean to execute that function, but it means to get a receipt, okay, of the program that tells what it could be, it could produce if executed. And if we adhere to the effect pattern, we can enable our program to use again the substitution model. It's not a direct infer. I can infer that I use the effect pattern, so I can use the substitution model, but we are narrowed then if we don't. And clearly the effect pattern was defined by someone, and this someone is Adam Rosian in his book Essential Effects. This guy is one of the main maintainer of the Katz effect system, so is somebody that knows a lot about the topic. And to understand if a type satisfy the effect pattern, basically we need to answer as those two question, which is what kind of effect the program will perform, and what type it will produce. The type can tell us this thing, and as we said, we need to separate the execution from the description of the effect. Fun fact, okay, Java probably was the first language on the JVM, on the first mainstream, okay, language that tried to, in some way, okay, there were the 90s, so, but in some way introduce a small effect system with checked exceptions, okay, because, they have not the deferred execution, okay, but they tell us exactly which are the effects that, for example, here, the read function, the read file method can access, because if it throws an IO exception, probably, okay, it have to deal with some form of IO. And then we have the return type of the function. So we have not the deferred execution, but we tracks the side effects, okay, with checked exception. The problem is that the architects of Java then lost their mind, basically, and from Java version 8 of Java, checked exception does not compose well with lambdas, and so nobody uses checked exception anymore. But there was it was the first example of mainstream in a mainstream language that uses an effect system, or at least try. Scala, to be fair, Haskell, okay, for first, but then Scala, and then Kotlin in some way uses monads to implement the effect pattern. Why monads? Well, because they basically satisfy the constraint that we have. We use the monad type. So here F to describe the effect, okay, that a function can perform, and the type inside the monad, okay, to describe the result of the function itself. Yeah, the problem, as we all know, I will not go deeper with monads, because it's probably it's a different. We can have a different talk, more than one probably. Okay, but if any one of you ever try to use monads, also the option or optional monad, or the try, the either, you know that without any syntactic sugar, we have to call flat map and map to compose different function that returns, okay, monads. Here, for example, we have a maybe int value that is an option of int, and if we want to use it, we have to call the map, okay. So composing function returning monads is not that easy, okay, and it's even harder if we have different monads. For example, you have an option and you want to compose with an either or with a try, okay, the hell. Just because I don't know if anybody of you knows what in Scala what the for comprehension is. Well, Scala architects understand in some way, also because Haskell understood before them, that the calling flat map and map is very cumbersome, okay, boring, difficult, also to read. So they added to the compiler some syntactic sugar, okay, the for comprehension. So the two syntax are completely equivalent. So this, okay, syntax. So we create as an option with 42, and then we read and the 42, and we use it to create a string is completely equivalent to this function. Okay, it's just the syntactic sugar that the compiler transform for us to make our lives easier. Lives, of course, sorry, easier. And what is an effect system? Now we know what the effect pattern is. We know why it's important. Now we have to understand what an effect system is. Basically, the effect system is an implementation of the effect pattern. So we have the pattern. As you know, the pattern describes the problem, but it's not the solution. Okay, the solution have to be instantiated. Okay, and here basically by a framework, and an effect system is roughly, okay, a framework that implements the effect pattern. So it has dedicated types to represent and express side effects. Basically, all the effect system replaces the side effecting operation in the standard libraries. So in Scala, okay, I don't know, the console, the random library are always replaced by the effect, because they are the function inside the standard library are mainly side effecting, okay. And then last but not least, they provides a way to manage effect, and for this reason they adhere exactly to the effect pattern. So now that we have done an introduction, we will focus on what Scala gave us, okay, which what is available in the Scala community, by the Scala community, for the effect system, and we will concentrate first on monadic effect system, so that is effect system that use monads to implement. Okay, I think that one of the first and probably one of the most known, okay, effect system, and maybe also not so much loved, but effect system in Scala is cut effects. Cut effects has only one type to express effects, that is the IO monad, okay, and we call it a Uber effect because basically inside the IO effect we express all the possible side effects. So we are completely blind of what kind of side effects a function can perform. The IO effect can fail only with trovable, okay, so only with exception. We can, if we want to create our own logic type error, or we have to create an exception, or we have to have an IO of either. Well, okay, it's a monad, so we have to use flat map and map to compose, and as many other all, to be fair, monadic effect system, they are both referential transparency because they use basically values to express programs, okay, which are exactly the instances of the IO monad, and they are lazy. So as a bonus, it implements a good. It has a good implementation of structured concurrency inside it, and I think that at the moment is the best implementation of concurrency we have in Scala right now. For sure, the most performant, as far as I know. So let's try to rewrite our junk flip function, okay, using the IO effects. So we have to use the for comprehension, as we know. And the first fact that we are seeing that when we read the signature of the junk flip function, we see that it will it could perform some effects because we return an IO, but we don't know which ones. Okay. And as we can see, as I said, an FX system replaces the parts of the of the standard library, okay, that can perform itself. So this random is a type of the Katz effect library. Then we ask for a first boolean, and if it's false, we rise. Okay, we create an exception. We fail with a runtime exception. Okay. And as we said, it's a recipe. So if we call the junk flip function, we are not executing anything. Okay, that is one of the main constraints on the effect pattern. Clearly, the library then gave us a lot of ways, to be fair, free, to run the effect, which is or extending the IO up simple type, okay, or using directly on the IO the unsafe run async or unsafe to future. And clearly here I'm called unsafe because you are effectively running the effect. Okay, so probably you will find this the call to this function, to this method in the main, okay, function of a Scala program or in the test, okay, never during in the business logic, for example, or in any other part of our program. As we said, the IO hides completely the exact side effects performed. There are some ways to explicit the effects, but we have to use a notation that it's EV, okay, to understand. It's hard to understand, which is tagless final, and we need some other library, okay. And in this way, we can return to add to the signature of our function the effects that effectively our program uses. Okay, so here, for example, we see from the signature that the jump flip function can rise, okay, a string, an array of type string, and will access to random number generation. Have to deal with non-determinism. Okay, but as we see, we can see we are elevating the cognitive load even higher. So Zayo takes the problems, okay, all the bad things of cut effects, and try to solve some of them, introducing more complexity in the type. Okay, as if you remember before, we have the IO of A, so we have an effective program that can fail with a throwable or result in a object of type A. Here we a program that an effective program that returns a Zayo of REA basically is a program that can fail with an error of type E, which can be anything, any type, that can return result of type A, and to execute needs some dependencies, okay, of type R. Also, Zio or Zayo, I think it's the correct pronunciation is Zio, but I also heard a lot of way call it Zayo.
For us that we are Italian, it's clearly Zio.
Exactly. And yeah, it's still a monad, so we have to deal with flat map for comprehension, okay, and it implements structural concurrent primitives. It's still a Uber effect because here, on the cut effect, we see we can run all the effects at once. We can choose which effects we want to run, okay? And for Zio is the same. For this reason, it's still a Uber effect. And if we try to write our drum flip function with Zio, okay, we see that now we have the two effects accessed by the function explicitly in the explicit in the return type, because here we are the type said that we are dealing with again with non-determinism, and we can fail with a string and we return a string, okay? But we have to still to use for comprehension, so map and flat map, and when we run, okay, we have to run all the effects at once, okay? Running an effect in Zio means to provide basically all the dependencies listed in the R type, and just to know, they are called layers, okay? Can we do better, or at
I have
least
a quick question.
Yeah.
Just for me, for curiosity, because I never used Zio.
Yeah.
If you go back to the other slide, like when assuming we have more dependency, let's say random and another one, let's say file,
we can use the intersection type.
I missed this. I missed.
Yes, I wrote it, but I didn't say that.
Interesting.
Scala has a good type system, okay? Very excellent type, maybe one of the best type systems among programming language. Rust maybe has something similar, okay? And it has intersection and union type, okay? So basically, if here I will say that Zio of random and console means that I need both random and console to provide both random and console layer, okay?
So they are still explicit. Okay,
yeah,
nice.
You can
don't
use
need a class, let's say, that contains both. It's
no,
automatically done. Okay, nice.
Exactly.
Thank you.
You can use product or some type.
Yeah, exactly, product and some type, but not at all, because an intersection type means that a variable that has this type is both a random and a console. Okay. By the way, can we do it? Can we do better? Well, there is some research, okay, in the last 10 years that introduces a concept that comes from mathematics, okay, exactly as monads, and try to apply to functional programming, and that are algebraic effects. Algebraic effects basically are a beast, okay, but for what we need, they are a way to listing effects separately, okay, and handle them once a time, each one once a time. So we don't need to execute all the effect at once, okay, but we can choose which effect we want to execute, eliminating from the signature of the function. And Kyo is I think in the Scala community, the main library. It's quite novel, but quite promising, that uses and implements algebraic effects and effects handler. In Kyo, we have, as we see, we list the effects separately, okay, again, using intersection type, okay. So here, drunk flip, we know that they have to deal with some form of non-determinism, okay. They don't have the random type. Flavio, I know Flavio personally, he doesn't like to add the random type, because he said that is not an IO for the random can fit better, okay. And we have a function that can rise, here said abort, with a string, okay. And the difference, okay, the difference, sorry, and we'll return to the previous slide in a minute, is that we can run each single effect, okay, separately from the other, okay. So basically here we are running only the abort part, and we return an effectful program that still need an I/O to provide an I/O effect. So to run also the partial result, I have to give it as an input to an IO.run method. Okay. Even the syntax is quite fancy. This type, this is a type, is still a monad. Okay. Is an alias for a monad, indeed, and we still have to use for comprehension. Okay, so we add the feature that we can eliminate, okay, delete each effect separately. Okay, but we still have to deal with monads. So can we do something different? Because as we see, combining function using flat map and map for sequencing is very cumbersome. Yeah, representing programs, effective programs as values, okay, gave us referential transparency, laziness, the full substitution model, because all the three effect systems we saw adhere also to the substitution model. We can use the substitution model when reasoning with them, because monads, because of monads, okay, not because of the effect pattern. But you know, as we said, if you ever try to use monads in production, you know that they are very hard to learn, and it's a beast that you need to understand very well. So can we do something, I don't want to say better, but at least different, something easier? Yes, we can avoid monads at all, and this is called direct style. So when basically day by day, if you use Java, you are using direct style. Okay, you are not using any monad. You are not composing function using flat map and map. So, for example, here, if you want to generate a random boolean, we are gonna call directly, okay, the function next boolean, and this will be the result of the function next boolean. But clearly, we lose the deferred execution, okay, and the fact that we want to track effect. So what can we do? We can return a function that, okay, requires an instance of random, and then, okay, call create, okay, the value as a function, returning a function. But you know, working with function, it's even harder than using monads, probably. Okay, but okay, as we will see in a moment, there is still hope. Okay, because Scala and also Kotlin, okay, introduces in the last versions some nice features about some special kind of function, okay, that can basically make our life easier, passing function here and there. So let's try to model an effect system using direct style. Okay, is it possible? Yeah, spoiler alert, yes, it's possible. But let's try one step at a time. First, we need the types. If you remember, a type that describe the effects. So in our case, in the case of the drunk field function, we need the random type and the rise. We will call it rise. Okay. So a type that represent that a function can fade with a type E, and type that represent that a function accesses to no determinism, here having a new boolean. Okay, then as we said, we need to replace an effect system need to replace the effective operation of the standard library of the language, and so we try to encapsulate, okay, the standard library in effectful operation. Okay, so we need to define our next Boolean, okay, function inside what? As we see here, we have a trait. So basically, this is an interface. We are gonna implement this interface calling directly the standard library random. Okay, and we call it unsafe because clearly it's unsafe to call it directly because it executes the effect and we don't the side effect and we don't want it. Then we need to create a DSL, okay, to let our effective program to access in a deferred way to the side effects, okay, and we can do it using givens or implicit in Scala. Okay, I don't know if anybody of you knows what are using and givens and implicit, and for the reason I added this slide. So what does this mean, this fancy, okay, syntax means? It means basically that the next Boolean is a function that takes no parameters, but to execute needs a context of type random, okay, a context parameter of type random that the compiler have to find somewhere, okay. It will search in the package, basically in the class, then in the object, the containing object, but it will try to find it, okay. In Scala 2, these features are called implicit. In Scala 3, they are renamed and improved in givens, okay. But basically, as we can see, we can create a given as in the same way we create a normal variable, and then if we call the next Boolean the above function, okay, without any parameter, okay, it will work because the compiler knows that in the scope there is a given of the same type, and it will pass, okay, automatically. Or we can also provide directly the given, okay, to the compiler. So basically,
it's like having a dependency injection.
Yeah, we can implement for sure dependency injection using givens and implicit. If you know Kotlin,
Yeah.
Is it Scala 3? Yeah. Is it completely Scala 3? The effect system we are creating is not possible in Scala 2 because in a moment we will see. Yeah, I will respond in a minute because we will use in the next slide a feature that is that was introduced with Scala 3, that are context function. Okay, givens have basically this more or less, okay, the same scope that implicit. Okay, so the compiler basically will look if it can find a given in the class first in the smaller scope possible, so in the same function, okay, if we are inside the function, then in a class, then in an object, then in the package object, and if we will not find it, it will fail during compile time. Okay, I don't know if I answer the question of Paul. So creating once we have our effect, our type, and our DSL representing the effects and substituting the effects in the standard library, we can rewrite our drag-free function, okay, in this way. So we have, which is called direct style. This is pure direct style. We have a function that needs to execute in the context a random object, an object of type random, an object of type rise of string, so it can deal with non-determinism and with failing with a string, okay, and it uses directly, okay, the DSL we created, and as you can see, okay, we are not using monads anymore, but there is some magic here, okay, because if you remember, this function, okay, needs a random to execute. So how is it possible? that the compiler uses can create and use a Boolean. Okay, this variable is clearly a Boolean. Okay, it's possible because of context function. Okay, context function are a feature introduced by Scala 3 in Scala 3, and basically are a fancy way to define anonymous function that has only context parameters. Okay, so here we see a function, a method, okay, having a context parameter. But if we want to define a lambda, which is not a method, because it's not a function, it's a lambda, it's a different type, okay, and we still need a context parameter, we can use a context function. Okay, the context parameters are the ones at the left side, okay, of this strange operator. So our drunk flip function, okay, can be stored in a variable, which is basically a context lambda, okay, and its type will be this. And if you see, these ones are the same types that we have in the context parameter list. Okay, so this notation and this notation are basically equivalent. Okay, the same. Only here we are using lambdas. Yes.
Well, do you think we are losing some information about the output type? I mean, because we are receiving the rise in input, but the output could be a string or an exception itself, no?
The output could be only a string and not an exception. Here you are saying, okay, you are saying that the jump flip function, the program, to be fair, the lambda is associated with the program variable. If executed, returns a string. Okay, and to execute needs a random object, which means in our FX system means something, okay, that can deal with non-determinism, and something that can rise basically an error of type string.
Exactly, but
so it's the same as a more or less checked exception.
Okay, but is in input, not in output.
No, it's not an input. You have to need these types in the context. Okay. You are not giving explicitly to the function. You are giving explicit to the function only when you want to execute it, but you don't want to execute it right now. You only want to define it, because when you are going to execute, you have to deal with side effects. So you have to be in a safe place. We are gonna look at it in a moment, okay? So basically, as we said, why this function now returns a Boolean without, okay, having, as Marco said, having in input any random object? Because this function is executed inside context, another function that has the same, okay, context parameter in its context. So the compiler will forward the same context, okay, to the next Boolean. And so inside the drunk flip function, we can basically extract a Boolean to CAF. But as I said, this is only a receipt. It's not the execution, okay? Okay, here a slide that said that this one is only, again, syntactic sugar to create other, okay, basically other types under the hood, which are not available to developers. So I cannot explicit create a type context function too. Okay, but no problem. And then also we have created a way to express an effectful program. Now we need the way to execute, okay, an effectful program, which is we need a handler for our program. Okay, and the run method is exactly this. As we see, we can see, the run method receiving input a program, okay, a block, a lambda that can raise an error of type E and returns an A. Okay, and here in the basic form returns or E or A. So this is a union type. Okay, and the union type is the other part of the intersection type. Okay, is the counterpart of intersection type. The intersection type said that a variable should be E and A in the at the same time. Here we are saying that is E or A. Okay, and again here we are using a special Scala free syntax, which are boundaries and labels. But basically here we are saying to traduce to translate, sorry, that raising an error of type P means creating, okay, throwing an exception, this bracket throwing a break exception of containing the same type. Okay, and this exception will be catched in by the boundary. So okay, we are circuiting here from here to here. Okay, and if we'll return the here we are executing the program because we have a given. So the given is forwarded to the program by the compiler, and order program succeed with A, or it will throw the break exception that will be catched by the boundary and return the E type. Okay, so just to say that we need a handler. Okay, and the handler is where the magic happens. So the handler is when we call the run method, we are effectively running our program in input. Okay. Whoop. And using handler as Kyo does, but here in a direct style way, defining different handlers with this for the same program can we can return different things. For example, if we don't like union type but we want to return an either, okay, we can just define a different handler. Okay, if we run our trunk flip function, okay, inside the either, with the header handler, we return an either of string because we can fail with a string and return a string. Just not changing our program, only changing the handler. And basically, it is one of the main points of using effect handler, algebraic effects and effects handler. Okay. Then here we are implementing also the handler for the random program, which basically uses directly the random implementation of Scala. And another thing we can do implementing different handlers, for example, is using handlers for test, for mocking. Okay, for example, we can have a test. We can execute our program with a test handler that returns, for example, a fixed Boolean in this case, or a fixed number. Okay, every time the next Boolean is called. Okay, just for test purposes. Then, as in Kyo, we have to run all the effects. Okay, to have the result. So here our junk flip function, you remember, uses the random and the rise effect. So we have to call the run and inside the rise, okay, and we have the result of an the either, an either of string of type string, and we are done. So basically we have implemented an effect system, okay, in direct style. We can say that this effect system uses a direct style effect handlers. I have not invented this definition. It's in the Unison language page. Okay, so if you don't know, Unison it's a language, a functional programming language for the cloud that was invented by the authors of the Scala Red Book. So people that knows a lot of things. Okay, it implements the effect pattern for sure, because we need two things. The execution must be deferred, and we have the deferred execution, and we have a type that needs to tell us which effects we have, and we add it, and which result, which is the result of the function. Okay, we can, if we like, we can define a type alias effect. Okay, and we clearly have this constraint satisfied, but we have lost completely referential transparency. Okay, and to prove this, it's quite easy. Okay, just extract, okay, the call to the next random next boolean function inside a val. If you do this with a monad in IO, in Katz effects, in Zio, or in Kyo, this will still be an IO, a Zio, okay, as a type. But here, the compiler, when we pass the true context parameter, when we run the drunk flip inside an handler, we will run immediately the gen run. So the caf variable and basically the heads will always see the same value of run, okay, because gen run is eagerly evaluated. Is it important? Well, if it's still important for us to have some form of referential transparency, which is mainly associated with monads and program as values, we can still have, okay, and you see, I just switch from val to def, okay, this variable. So this variable is not a variable anymore, is a def, so it will be executed every time, okay, the compiler will find it. And so we introduce again some form of referential transparency. But do we really need the referential transparency in our day-by-day work? Well, probably, okay, 80% of the times we don't need it. Okay, we just what we need is the deferred execution and the fact that we are able to track effects. Okay, so we lost something, but we gain something else. So there is not free lunch, no silver bullet now in our world. So it's some form of balancing. Okay, we have to understand when to move, okay, the complexity. Do we want to move the complexity inside the monad? Because if we have not the monad, we have to have less constraint, okay, or to find somewhere else to put the complexity. And here we have to relax, okay, clearly our constraint, and we losing, ahimè, in Italian, referential transparency. Okay, just to sum up, if we want to reintroduce an IO effect, we can. What is an IO effect in a direct style effect system? Basically, is something that can run, okay, a program in a separated thread. Okay, if we are running on Java, okay, Java 24, Java after 19, to be fair, we can use directly virtual threads, okay, to run it, and it's quite good because virtual threads are implements delimited continuations, okay, and it's something that we really like because it's really similar to what the direct style gave us. Somebody says that direct style effect systems, okay, are syntactic sugar over delimited continuations, okay, but it's still not proven as far as I know, and just words, okay, for now. And as we said, if we want, also an IO can catch every unchecked the exception that any bug, okay, that a program can have, okay, it could be the last frontier, okay, to try to manage, okay, an exception that we didn't expect. What I've done is for now is creating a direct style, completely direct style system. But if we want, we can add flat map and map as extension function, okay, to our effect type. Okay, so if you remember, we have defined here the effect type. Okay, it's only a type alias on the context function. And if we if we are able to define flat map and map on a type, basically we can use again for comprehension. Okay. Do we reintroduce referential transparency? No, not at all, because once the compiler desugar this, it returns to we return to have completely direct style. So it's only a matter of which syntax I prefer. Okay, but having for comprehension here does not bring us all the fantastic feature of monads. Okay, without the complexity, it's not possible, as we said. So just to sum up, and sorry, probably I'm late. Okay, what we did is that we defined what the side effect is and why we don't like it. We introduced the effect pattern, the effect systems. We saw how the Scala community implemented such effect system using monads, okay, with success, with an enormous success, a huge success. We introduced algebraic effects, monadic algebraic effects through the Kyo library, and then we built our own effect system using context function and direct style effect handler. Okay, and we saw, last but not least, how we can still using for comprehension, okay, for our new effect system. And by the way, all the stuff that I present is actually implemented in a library that I'm developing right now with some other good guys, okay, that is called YAES. And if you want, you can collaborate with me and add some stuff, because it's a project, an in-process project, okay? So, Godspeed, farewell, and thanks for all the fish.
Okay, we have done a travel of like 10 or 3 books of like 400 pages in like 1 hour. So I hope that at least the people that are with us are read at least like the half of these books that you have presented in this slide. So
I try to make it easier as possible.
There are, I think, a couple of questions. There was a discussion about the languages with the strongest type system, which there is which we can leave it offline.
I have not to say what I said.
No, but was fun. So there is some question from Paolo. Yeah. So one is this: is given in Scala similar to the context receiver in Kotlin?
Yeah, exactly. The difference is that context receiver now context params in the new version of Kotlin are not resolved automatically by the compiler. You have to provide it explicitly with the with context function, for example, but are exactly the same. And in fact, the RISE I made 1 year ago. I made another library which then evolved to YAES, which is called RISE for S, and it's exactly a port of the error KT RISE type, which is a functional library for Kotlin in Scala. And there is exactly a one-to-one equality between context receivers and context function in Scala, but the only difference is the compiler resolution.
Perfect. There is another question from Angelo. So Scala futures are eager to and support monadic operation, right?
Yeah, futures are future does not implement the effect pattern exactly for this because they not defer the execution. When you create a future, the execution starts in that moment, okay, and will end in the future, okay. So futures are not monads at all, and you can't use it to create an effect system, more or less, because right now the people at the Scala Center are creating Caprese, okay, which is the next Scala, okay, thing, which basically will use same concept as me, but on top of futures. But it's still it's 2 years that we are waiting to see what the Caprese is, also because they introduced the concept of capabilities. It's quite difficult. We are waiting to see what's going on, but yes, future, you can't use future directly to implement an effect system.
The discussions in the Scala community are quite hard, typically.
Yeah, also because there is a lot of drama in the Scala community. A lot of drama.
We will see this Caprese like in 5 years in Java, but simplified. It's not simplified.
Probably. You know, Java is a really game changer for all the JVM program because you know, if you can, why Kotlin coroutines are so beautiful, you know, because you have a continuation, but it's the compiler that takes care of the continuation at all. So you don't have to use monads and deal with all the composing stuff. It's the compiler. So if you can move to the compiler some concept, for example, virtual threads are more or less the same, but they do not expose directly the continuation DSL. Every program running on the JVM can improve, okay, and take advantage of this. So we need Java to have a better language. We need Java to evolve.
Yeah, because Java is a better language. So
Giovanni now
I'm
has
joking.
the eyes with the heads. We can see.
Okay, any other question?
Let me see. No, people having fun, trolling, and they are very happy about the topic. I think if there is no more question from us and from the audience, I think maybe we can close with this message from Arialdo. And so thank you all for being here. Thank you, Riccardo.
Thank you.
And see you in the next meetup.
Yeah.
Bye-bye.
Bye-bye. Bye, everybody.
Bye.
Bye.